Alrighty folks, in this video we're going to learn how to calculate limits analytically. What that means is instead of looking at a graph or a table, what if they give us a function? How do we find a limit of a function, basically? Alright, so before we can jump into that, we have to go over a little bit of background information. So the first thing I want to talk about is this thing called a rational limit theorem. Okay, and so what that's saying is that if x equals a, so remember our limit is as x approaches some number a, if that value a is in the domain of our rational function f of x, then it turns out that the limit as x approaches a of f of x equals f of a. So what does that mean? I like to call this the plug and chug theorem. Because what this is saying is that if that value is within the domain of that rational function, to get the limit, all you have to do is plug in that value, right? However, that only works when x equals a is in the domain. So it turns out, let's get into some extra notes here. It turns out that a limit may exist as we approach a hole. These holes are also called removable discontinuities. So if you remember from the video on limits of a graph, you notice that even if we had a hole in the graph, we would still have a limit as we approach that value. So that's what we're going to have to account for in a second. I'll show you how to do that. And so if you remember back in your algebra days, we get a hole whenever a factor cancels in a rational function. I'll show you what I mean by that in a second. However, a limit will not exist as we approach a vertical asymptote. Quickly, what do I mean by that? Let me show you the two different examples here. Let's say that we have a vertical asymptote at x equals, let's say, 2. All right. So the limit as x approaches 2, right, will not exist. Why is that? Because if you remember from back in the day, a vertical asymptote, when you approach a vertical asymptote, you can either go up infinitely or go down infinitely. Remember we said that limits can't be infinite. So that's why a limit as you approach a vertical asymptote, it does not exist. However, let's say we had a hole in the graph. Let's say we had a hole in the graph right here. And our function is something like this. And let's say that hole has a height of about, let's say, I don't know, 3. And let's say that x value is 5. So I'm just making up numbers here, and technically speaking, that's a hole, so there's nothing there. But if we were to ask to calculate what's the limit, the two-sided limit, as x approaches 5 of our function, that limit will exist, and that limit will equal 3. Because remember, limits do not care about holes. They only care about the approaching behavior, the trending behavior. All right, so I keep on talking about rational functions. So a rational function just means you have a function that looks like a fraction. Okay. If you attempt to do a plug and chug, meaning you try to plug in that x value and you get the limit being 0 over 0, we refer to that limit as being indeterminate. And what does that mean, as the name implies, is that the limit cannot be determined by simply plugging in the values there. There must be more work to be done to determine if a limit exists there. And for us, spoiler alert, that means we're going to have to factor and cancel out some things. What I'll do is I'll make sure I drop a link to the to my factoring video as well if it's been a while since you factored. Okay, here we go. So for example, they want us to find the limit, and all of these will be two-sided limits. I will say that all of these will be two-sided limits. Find the limit as x approaches 2 of x squared minus 4x plus 4 over x squared plus 6x minus 16. Okay, before evaluating that limit, what I want to do is to kind of remind you about how we figure out holes and vertical asymptotes and domains and things of that nature. Okay, so really quickly, I want to go over just kind of some analysis of this. So let's say f of x equals that function, x squared minus 4x plus 4 over x squared plus 6x minus 16. And in fact, let's go ahead and factor both the numerator and denominator. In fact, factor anywhere that's possible. So for x squared minus 4x plus 4, I'm looking for a set of numbers that multiplies the positive 4, but sums to a negative 4. Okay, well, x minus 2 times x minus 2 should do the trick. right? Negative 2 plus a negative 2 is a negative 4, and the negative 2 times a negative 2 is a positive 4. And then in our denominator, that appears to factor into, let's see, a set of numbers that multiplies to negative 16, but sums to a positive 6. It looks like x plus 8 and x minus 2 should work out. Okay, so right now we fully factored out everything. Do not cancel. Yes, the x minus 2's will cancel, but we're trying to figure out the domain really quickly. So the domain for this will be all reals. If you recall our domain video, all reals except for the values of x that create a 0 in the denominator. So what do? We remember we take both of these factors in the denominator, just the denominator, and we set them equal to 0, which gives us solutions of negative 8 and positive 2. So that indicates that our domain will be all reals except for those two values, a negative 8 and a positive 2. All right? So now let's talk about a hole. Let's talk about a vertical asymptote, because your holes and VAs are directly related to the domain. In fact, the hole and the VA, the locations of those, the x values of those, can only be the exceptions, the x values that we're leaving out of our domain. So how do we know if we have a hole? Well, a hole occurs, as I said earlier, when a factor cancels. Well, we saw before that x minus 2, or we see now that x minus 2 is going to cancel. So that means that when you take x minus 2 set equal to 0, you get x equals 2. That means that since that x equals 2 cancels, x equals 2 is what we call a hole. And that's where it gets its name removable discontinuity from, because we can, it's a hole, but we can get rid of it from the function. Okay? And so what does that mean? That means that we are now left with the function, the simplified function of x minus 2 over x plus 8, right? That's our f of x. And your vertical asymptote is the exception that doesn't get removed. It's permanent, so to speak. All right. And so since there's no way to get rid of that x plus 8 in our denominator, once we set that equal to 0, we get x equals a negative 8. That means that our vertical asymptote is x equals a negative 8. Okay. So really quickly, how do you figure out your hole in your VA? Figure out your domain. Factor everything. Don't cancel, but do your domain, and then you figure out what are your exceptions. What do you leave out of your domain? From those exceptions, okay, each exception is going to either be a hole or a VA. You have to use up all of those exceptions. They're either going to be a hole or a VA. How do you know if it's a hole? Well, if the factor cancels in the original function, it becomes a hole. If the factor does not cancel, then it becomes the VA. Okay, the vertical asymptote. All right, so now that we know that, now let's talk about the actual question here, the limit. So how do we find the limit as x approaches 2? Well, now that we see this, we see that, hey, since we're approaching 2, we're approaching a hole, which is perfectly fine. We can have a limit at a hole. So what you do now is you take the limit as x approaches 2, and we're going to plug it into our simplified function, x minus 2 over x plus 8. Okay, and I'll show you why we have to do that in a second. So now x equals 2 is now within the domain of this because we got rid of that removable discontinuity. So now what we could do is we can plug and chug. We can plug in this x value of 2 in for x. So you get 2 minus 2 over 2 plus 8, which is 0 divided by 10, which equals 0. And yes, that is a legal number. Okay, so the limit of this function ends up being 0. All right. And let me show you what happens if you try to plug in 2 directly into that limit there. All right, so the limit as x approaches 2 of the original function, x squared minus, 4x plus 4 over x squared plus 6x minus 16. I bet you're going to get an indeterminate form. Why is that? Because at x equals 2, that's not in the domain. Check this out. You get 2 squared minus 4 times 2 plus 4, clean that up in a second, over 2 squared plus 6 times 2 minus 16. So really quickly, in the numerator, we get 2 squared, which is 4. You get 4 minus 8 plus 4 over 2 squared in the denominator is 4 plus 12 minus 16. Let's see, 4 minus 8 is a negative 4. Negative 4 plus 4 is 0. Divided by 4 plus 12 is 16. 16 divided by 0 is 0. And please note, if you don't take anything else from this lecture, please note that this does not equal 0. This is what we call an indeterminate form. Okay? This means that this could be anything. It could be a limit of 0. It could be a limit of 10. It could be a limit of negative 3/5. It could be a limit of 5. It could be a limit that doesn't even exist. So when you get to 0 over 0, you cannot automatically say that that limit is 0, or you can't say automatically limit does not exist. Okay, that's when you have to factor and do some additional work. All right, here we go. And just for the sake of completeness, let me show you what happens. One more. What if instead we wanted to know the limit as x approached 8, negative 8, that vertical asymptote? Okay. And once again, I'm not going to do the whole work here, but if we plugged in a negative 8, once again, we get 0 over 0. So when you get 0 over 0, that means you need to factor and cancel out something. So let's just plug it into the simplified version, right? The already factored and canceled version. So now if I try to plug a negative 8 into this, I get a negative 8 minus 2 over a negative 8 plus 8. And I get a negative 10 over 0, which is undefined. Okay? So what this means is that the limit does not exist. Why is that? Because we are approaching a vertical asymptote. Can't stress that enough. Negative 8 is a vertical asymptote. That's why the limit is not going to exist. All right, let's get into one more. Here we go. Find the limit as x approaches 3 of x minus 3 over x squared plus 6x minus 27. So we know the drill. Let's go ahead and let's go ahead and factor where we can. So that means let's see if we can factor that denominator. Let's see. I need to multiply to negative 27, but sum to 6. So that is a positive 9 and a negative 3. Okay. So once again, if you want to keep track of your domain and holes and VAs, so your domain will be all reals except what? Except a negative 9 and a positive 3. Why is that? Set that denominators, both those factors, equal to 0. When you find your domain, don't cancel anything, because if something cancels, it now becomes a whole. So what cancels? The x minus 3 cancels. And that means that we have a whole at x equals 3. Remember, you're setting that factor equal to 0. So it's not a negative 3, it's a positive 3. Which indicates that we're going to have a vertical asymptote at x equals a negative 9. Because once again, we have to use up all of our exceptions. Each exception will either be a whole or a VA, but they can't be both. All right, that being said, let's go ahead and write down our simplified limit here. So it's the limit as x approaches 3 of, now be careful now, there's still going to be a 1 remaining in the numerator, over x plus 9. Okay, so now we are able to plug in an x value of 3. Why is that? Because now 3 is in the domain. 3 is not going to mess up this function. So 1 over 3 plus 9 means that our limit is 1/12. Okay. Once again, if you go to the beginning and you try to plug in 3, you're going to get 0 over 0. And apparently this time, 0 over 0 ended up being a 1/12. That's what we mean by an indeterminate. Okay? And just to make sure you guys are good with these VAs, what if it was the limit as x approaches a negative 9 of our function? Okay, I'm going to write the simplified function, 1 over x plus 9. Well, that's automatically, that limit is not going to exist. Why? Because x equals a negative 9 is a vertical asymptote. Okay. So folks, that's how you're going to find your limits analytically, okay? You're going to have to do some factoring, some canceling, and then plugging in your x values, okay? If you're approaching a vertical asymptote, your limit will not exist. If you're approaching a hole, the limit will exist, and you find it by plugging in the x value. All right, see you guys in the next video.